Okay, I'd like to finish the explanation of electroscopes that we were doing yesterday in class. All right, so I just happened to have brought an electroscope home with me. So Alyssa, because you weren't there yesterday, this is what an electroscope actually looks like. Those are the little thin leaves that are hanging at the bottom, and they're foil, and they're really light and fragile. So when I bring a rod closer to the leaves, and if it was charged, I just don't know that I can do that. Fluffy's here with me, in case you were wondering. I only have one hand is the only thing, so I can't really rub Fluffy, hold the iPad, and build up a charge here. So you're going to have to believe me that there's a charge. Okay, let's try one more time. So here's the, no. So there are two different ways of charging this electroscope, okay? One way is when you bring the rod close and you don't actually touch it to the electroscope. And that's what we were doing yesterday. Okay, so this is called charging by induction. So we're inducing a charge. We're not actually changing the overall charge of the electroscope. So if we bring a negatively charged rod, I'm going to draw it up here. This is negatively charged, close to the electroscope. The electroscope is made up of metals. Metals do not hold on to their electrons well. They actually share them among their friends and neighbors. If you think about their valence shell, metals tend to need 4 or 5 to get a full valence shell, and that's really hard to get. Like if you think of the chlorine and those guys, they only need 1. So they can steal 1 and get a full outer shell, no problem. The next row, oxygen in them, they only need 2, and they can steal 2 and get a full outer shell all as well. But when you get to metals, they need 4 or 5, so they feel like they're subject to never being complete. And then one day, this little metal was like, hey, what if I give you 4 of my electrons and you give me 4 of yours? They said to one other metal atom. And so the other atom agreed. Now you might think this is not very smart, but they both put their electrons kind of in between them where they could both see them. So the first atom was like, oh, look at my electrons. And the other atom, looking at exactly the same ones, thought the same thing, and they both felt complete. So then it didn't take long before the other metal atoms were wanted in. So they all just dumped their electrons together, and those electrons are free to move around each other. I usually say it's kind of like a commune back in the 70s or 60s. Now, I don't remember them, so you probably don't remember them, but I know I've heard of them. And so people would live together and they would just put everything together, including their kids. So imagine that there was a commune in your subdivision. So everybody just dumped everything together and everybody looked after everything together. So if you happened to stop by to visit one summer day, you'd see all these kids playing on the street outside. Then you'd see like one poor woman come out and bring them all a snack. And you'd be like, wow, that poor woman has like these 20 kids? That's incredible. But then if you waited long enough, you'd see at lunch that it was a different woman that came out and looked after them and a different parent. So it would be impossible to tell which kid belonged to which house. And that's the same with the electrons in a metal. It's impossible to tell once they're together which electron belongs to which molecule. They're just free to move around. And that becomes important here when we bring a negatively charged rod in close to this electroscope. Because all of the electrons in here that are free to move around are like, oh no, a big, nasty, negatively charged rod is coming. Run away, run away. And so they do. They all run away, as far away as they can get, which is down here into the leaves. And it causes the leaves to spread apart because they both become negatively charged. And it leaves behind on the ball of the electroscope a positive charge because all the electrons are down here. As soon as the rod is removed, they're like, oh, it's gone. And they all move back up to where they were. Okay, so the overall charge on the electroscope doesn't change. It's just where the electrons are that changes. Exactly the same thing happens if it's a positively charged rod I bring in. Well, almost exactly the same. Except this time the little electrons are like, oh boy, there's there's a positive charge rod coming. Come on, everybody, let's go. And they all run up into the ball of the electroscope, making the ball of the electroscope negative and leaving behind on the leaves positive charge, which then causes them to spread apart. Again, as soon as the rod is taken away, everything goes back to Morrow because there's no overall change in the charge of the electroscope. And so it's called charging by induction. That is different than the second type of charging, which is charging by conduction. In conduction, we don't just bring it close, we actually touch it. Okay, so we're going to touch the rod to the electroscope. So again, if this rod is negatively charged and we touch it, remember if you have two different objects with different charges, there's going to be a transfer of electrons. So the rod is negatively charged, so the electrons are going to flow from the rod to the electroscope, giving the electroscope an overall negative charge. If it has an overall negative charge, it means both leaves are negatively charged and they spread apart. When we take the rod away, they stay apart because we've actually given the electroscope more electrons. So it has a net overall negative charge, and it will stay that way until some object comes along and touches the ball of the electroscope, which causes it to then go to neutral, and that's called grounding. When you touch something to take the excess charge off, we ground it. Okay? So the electrons come over and then they spread out and they stay there even when the charge is taken away. If the rod is positively charged that we're bringing in and touching, then the same type of thing will happen, except this time the electrons go from the electroscope to the rod, leaving behind on the electroscope a net positive charge, which means both leaves will be positively charged and they will spread apart. When the rod is taken away, the electroscope has a net positive charge left on it and the leaves will stay apart until again something comes along and grounds it. Okay, so notice it's always the movement of electrons. When the rod's brought close, there's no transfer. The electrons just run from it or run towards it. But when there's an actual touching, then there's a transfer of the electrons from one object to another, leaving an overall net charge, which will stay on it until the object is grounded. Okay, so that is the end to the test. I am going to do one more video, which is the new stuff, but it will not be on the test. It'll be on the test after Christmas. Okay, thanks.